Hello, good morning, everyone, and welcome back to CS300 Introduction to Algorithms. Today we're going to wrap up chapter 5 on graph problems. So let us have a look at the graph problems we have been considering so far and recall the state of our knowledge. So the graph problem we have been considering is a maximum flow problem. So let me review specification according to our virtue of computer science specification first. So the input is a directed graph with possibly with edge weights, and the edge weights indicate kind of the capacity of pipes that can carry some liquid, and the goal is to push as much liquid as possible through this pipe system from the source to the target. And while observing the constraints, namely the maximum capacity of each single pipe. So this is a maximization problem with constraints, and the constraints are kind of labels to the pipes modeled as directed edges with non-negative integer weights here. One can also consider non-negative real weights, but we will see in a minute or 2 minutes why we restrict here to non-negative integer weights. So what we've observed already is that there's a kind of there's a formalization of what is a flow. A flow is something that enters in the source vertex and ends up in the target vertex, and on all other internal vertices obeys this continuity equation, basically saying that no liquid is lost at any node, nor is there liquid inserted at any node. And therefore, it seems intuitively clear that anything that enters through a source node must also leave to a target node. This is not a mathematical proof, but a physicist proof. I am a physicist, so please bear with me. Thanks for you indulging. So, and the flow is admissible if it obeys the limitations imposed on each pipe, the capacity. And the goal is to calculate a maximum flow, namely an assignment of how much liquid to pass through each pipe that satisfies the continuity equation, that adheres to the admissibility constraints, so no pipe will burst, and that is maximal as much liquid as possible to leave the source vertex and to enter in the target vertex. And here we've considered the first algorithm, the Ford-Fulkerson algorithm, which actually, as I will show, not technically an algorithm. We've seen here in execution, and the basic idea of Ford-Fulkerson is to consider the residual graph of the original graph with respect to an admissible flow. The residual graph is basically the graph with all edges removed that are already at their limit, that carry already as much liquid as is admitted according to their capacity. And so removing those edges that are already at full capacity, we cannot use those edges anymore in order to further increase the flow. That's the intuition. Whereas the other remaining edges that are not yet at full capacity can serve to possibly further increase the flow. So this is a kind of a meta approach. The typical maximization algorithm is kind of a greedy algorithm. It looks at the initial data and calculates the partial maximum, and then tries to improve that to get a larger quantity and so on. And this is also what's happening here. Only here there's a kind of not one element by one element, but one path by one path. Namely, in the residual graph, Ford-Fulkerson algorithm will look for a path from source to target, and that path can be used to further increase the flow. Therefore, it's usually called an augmenting path. So a path from source to target vertex, where the flow kind of increases by pushing additional liquid through that path. So for this purpose, Ford-Fulkerson repeatedly performs connectivity search using, for example, Dijkstra, and then determines how much liquid can go through that additional path. And we see here an example iteration, example execution. First execution considers this path, which is then pushed to its maximum capacity. Originally it was empty. This is not depicted. The maximum capacity is 2. This is the bottleneck. This pipe can hold up to 3, but there's no use for that here, because this pipe is the limiting factor. So amount of flow 2 is pushed through that path. Then next iteration, this augmenting path is considered. This path is already, this edge is already absent, right? This edge is removed from the residual graph. It's already at full capacity. Therefore, this path is not available anymore, but this path is still available and is used in this example execution in order to further increase the total flow by pushing additional amount 2 through this path. And here, this edge is the bottleneck. This edge could bear more, but this is the bottleneck. So now this edge gets also removed from the residual graph, this and this edge, so that only this path remains, which we can see here. And this is indeed what this example execution of Ford-Fulkerson pursues and considers in the third round. Along this path, this edge has been almost at full capacity, 2 of 3. So there's only room for one more unit. Same for this edge, there's only room for one more unit here. And this edge has capacity for 5, but we cannot harness that fully. Instead, it's only one unit of flow that passes through that edge. So this is the third augmenting path, and then the removing also this edge and this edge makes the residual graph disconnected, right? After having removed these 2 edges and now also these 2 edges, there's no path anymore from source to target. Only this edge remains, and that does not constitute a path. So this is where Ford-Fulkerson stops and has arrived at the flow of value 5, right? 2 here, and first 2 here, and then another one here, making 3 here. So total amount of 5 units from source, and of course also 5 units into the target, because nothing gets lost according to the continuity condition. So here you see a informal description of Ford-Fulkerson. Start with a trivial, the empty flow, nothing Pantare, right? Nothing flows. No, that's not what Pantare means. But anyway, initially nothing flows, and then find some path from source to target in the residual graph. This is a residual graph. Calculate the flow feasible through that path. This is much easier than calculating, in a sense, right? I mean, calculating the maximum flow in the path is easy. Just take the minimum, the bottleneck over all edges, according to the remaining capacity This is the capacity, and this is what is already flowing through the edge, and the difference is what can be used for augmenting, and then add that to the original flow, because calculating the maximum flow along a path is easy, and Ford-Fulkerson kind of on a high level perspective reduces the problem or solves the problem of calculating the maximum flow in a graph to the problem of calculating the maximum flow in a path repeatedly for different paths, namely each time for another different path in the residual graph. And this also leads to an analysis, runtime analysis of Ford-Fulkerson. How long will Ford-Fulkerson run? Well, there's this big loop while there exists some path, then exists some path. This is an invocation of Dijkstra's algorithm, which runs in time proportional to m, the number of edges. So the huge question is, how often is this loop executed, right? Each execution takes cost O of m for an invocation of Dijkstra's algorithm, which is implicit here, right? This is not pseudocode anymore. This is a more high-level description of Ford-Fulkerson. And so the question is really how often this outer loop gets executed. And the answer, our first observation, is that during each execution, the current flow increases by at least 1. Let me say that again. Each execution of this while loop increases the flow by at least 1. Why is that so? By the very definition of a path in the residual graph means that there is a path which has capacity, and since we're talking about integer capacities, that means the capacity of that augmenting path is at least 1. This minimum is at least 1. So it cannot be 0, because 0 means that the edge has been removed from the residual graph. If the flow is already equal to the capacity, then that edge will be absent and therefore will not occur in the path. Therefore, all the edges occurring in this path here have capacity strictly greater than the current flow. And since we're talking about integers here, strictly greater means at least 1. And this is important, and this is a reason why we don't consider real weights or real capacities here, because when a real capacity or residual is positive, it can be arbitrarily small, right? Like up to epsilon. But here with integer capacities, the residual flow has value at least 1. And therefore in each iteration of this loop, the total flow increases by at least 1, And therefore the number of iterations can be bounded by the total flow, the output, right? So this is the value of the output flow, and m is to denote the execution or call to Dijkstra's algorithm. So each iteration corresponds to or amounts to one call to the, or one execution of the increase of the flow by 1, and therefore the total flow increases by at least the number of iterations is at most f, the output flow. So right, let's briefly address correctness. Anything that Ford-Fulkerson calculates is a flow, right? And why is it at a maximal flow? Because when Ford-Fulkerson stops, there is no augmenting path remaining. So that's SRH correctness. And here we have an upper bound for the running time. And that's a kind of terrible upper bound if you look at it. It's terrible. Why is it terrible? Because Yeah, because there's no actual upper bound on the value of the total flow here, right? So there's a true upper bound, maybe the largest edge capacity, or the least, yeah, I'm going to say the largest edge capacity that occurs at all in the graph, but that can be very large. And remember that we measure our running time usually not depends on the value of the edge weight, but in dependence on the binary length of the input. And remember that there's a exponential difference in general between both. So in generally, the 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 value of the total flow is exponentially larger than the binary length of the input, and therefore this running time bound is boils down to being exponential in the input length, which of course is bad. And that raises the question, maybe we're here overestimating the actual cost, right? It's quite conceivable that our estimate, right, our bound is unnecessarily conservative, that the actual running time is much better, but unfortunately it's not, as illustrated with this admittedly artificial example, but it is an example where Ford-Fulkerson indeed takes a number of iterations that is exponential in the binary input length, or put differently, that is linear in the value of the edges. And again, so this example again considers the simple graph that we had previously, but with different edge weights. Namely, this edge here has weight only 1, capacity only 1, can carry only 1 unit flow, whereas this edge and these edges all have capacity which is very large. Here it's indicated with 1000, but this is just a symbol for something that has a very large capacity. Now let's consider Ford-Fulkerson run on this graph. So let's say Ford-Fulkerson starts with this initial augmenting path, as you can see here. This augmenting path has capacity only 1 because it uses this edge, which is limiting, right? So it cannot really harness the full capacity of this huge, large pipe with capacity 1000, because here's the bottleneck. So after first iteration, the flow has increased from initially 0 to 1. And let's now consider the next iteration, where Ford-Fulkerson has removed that edge from the residual graph and now considers this path. And this is an important subtlety and gives me the chance to expand more on that. Namely, remember our subtle definition of the residual graph. The residual graph contains all edges which have not exhausted their capacity, where the current flow is strictly smaller than the feasible flow, or the edges where the converse, the reverse direction, right? So this is an edge from U to V, this is from U to V, but this is an edge from V to U, so it's in the opposite direction. And the condition is here, if the edge in the opposite direction has a positive flow. And this is actually what happens here. So this edge in this direction has flow 1. Therefore, in the opposite direction, it has flow -1. So this is a subtlety I need to explain a little bit more detail. Namely, we're talking about directed edges here, right? So in the flow going into one direction of this directed edge, let's say flow 1 in this example, can also be considered as a flow in the opposite direction with a negative amount. So we're deliberately also allowing and considering flow to go through directed edges in the opposite direction. And we consider this by considering the negative sign, assigning a negative sign to such flow. Let me say that again. So superficially, the flow must go in this direction, the direction of edge, with a positive amount, a positive flow, but it can also be considered as going into the opposite direction with a negative amount. And more generally, we allow our liquid to go in both directions of an edge. One direction counted positively and the opposite direction simply counted as a negative flow. Right. So, and this is used here, namely, so this edge is now part of the residual graph, but in the opposite direction. So in this direction, it has been exhausted. So this edge has been removed, but instead the edge in the opposite direction is being added to the graph, to the residual graph, because one can push negative flow into this direction, which basically means that two flows can cancel, right? So flow unit 1 in this direction and the flow of unit 1 in the opposite direction basically means that the two flows cancel and nothing flows. And that's reasonable physically. And we use that here algorithmically in the definition of the residual graph with this second condition that I now had the great opportunity to finally explain. So, and this also now clarifies the second round of this example execution of Ford-Fulkerson, where Ford-Fulkerson considers this residual path following this direction, edge in direction, following this edge in opposite direction, and following this edge again in direction. And here, opposite direction and in direction constitutes an augmenting path of capacity 1, because remember that this opposite edge has capacity 1. This edge has exhausted capacity, so in this direction it has already no free capacity, but in the opposite direction it has capacity 1, and therefore the path is this augmenting path is considered and equipped with capacity 1, so that now this edge receives a flow of 1 and 1. So to now the second round of this execution of Ford-Fulkerson, the total flow has increased from 1 to 2. And then comes the next iteration, which is omitted here, but it's the same as here. Ford-Fulkerson considers this path again, right? Remember that this edge here has been used with flow 1 in this direction, but here a flow in the opposite direction of magnitude 1 has been assigned, and the two flows cancel, so that there's no flow after the second round, so that in the third round the same flow can pass through the network again. And then the fourth iteration, again the edges proceeded in opposite direction. So alternatingly, these two pictures emerge in augmenting path, and in each iteration, one unit of flow gets added, so that in this example, really the number of iterations of Ford-Fulkerson is proportional to the maximum flow, whose value is 2000, right? We can see that 2000 here, 1000 here, and 1000 here. Okay, so that means that we have not actually overestimated the computational cost of Ford-Fulkerson. It is proportional to the final maximum flow, and therefore, yeah, this is unfortunately the actual estimate. But this example also exhibits why this happens and how we can avoid this. Why does this happen? Because Ford-Fulkerson has several augmenting paths to choose from in the residual graph. So in this example execution, it takes this augmenting path, which has only capacity 1 due to using this edge, but why not use this augmenting path, right? This is also perfectly reasonable, this augmenting path instead of this. Why not use this augmenting path? Because there's no specification which augmenting path Ford-Fulkerson uses. Just takes any augmenting path feasible in the residual graph. And this is emphasized here, why there exists some augmenting path. And this is why Ford-Fulkerson technically is not really an algorithm. It's not fully specified its execution, right? There's some kind of randomness or non-determinism inherent to Ford-Fulkerson, and if that non-determinism is used in an unsuitable way, in a strange way, then it can lead to this very inefficient behavior, where in each iteration the flow increases by only 1. On the other hand, it would be much smarter from our global perspective to immediately use this augmenting path, which would jumpstart the flow from 0 to 1000 in only 1 iteration, and then use this augmenting path to add another flow of magnitude 1000, and thus reaching 2000 in only 2 iterations. So the message to take home from this slide is, depending on which augmenting path Ford-Fulkerson uses, it seems that the number of iteration can either be very large, exponentially large, when there's only increase by 1 in each iteration, or can apparently be very few iterations, just depending on which augmenting path is chosen. And one rule for making the augmenting path kind of fully specified is to use the shortest augmenting path, right? So looking at the examples again from this perspective, this augmenting path has 3 edges, so it has length 3, whereas this augmenting path uses only 2 edges, it has length 2. So this seems to be preferable. This is still a heuristic, but this heuristic already has a name, namely the name Edmonds-Karp, named after Jack Edmonds and Richard Karp, famous computer scientists. And so this is kind of a specification of Ford-Fulkerson, namely not take some augmenting path, but take a shortest augmenting path. And at least in our example, this seems to accelerate drastically the number of iteration. And all that's proof that the Edmonds-Karp variant of Ford-Fulkerson indeed has running time, which is finally polynomial in the input parameters and not exponentially anymore. Namely, the statement is that the running time is linear in n times m squared, n as usual denoting the number of vertices, and m the number of edges. And the observation to this end is, again, right, so we have a each execution of Dijkstra to find the shortest path is contributes with an m here, so that the statement is actually that the number of iterations is n times m, and the additional m comes from finding a path according to Dijkstra. So why is the number of iterations n times m? And the observation here is that every edge that is used once in an in a shortest augmenting path will actually decrease the distance from source to target vertex. And since the distance from source to target can be at most m, this means that there are at most, any edge can be used at most n times. Let me say that again. So the statement is that each iteration here uses some edge. An edge could possibly be used several times, but each time an edge gets used, it changes the in the residual graph, it changes the distance from source to target. And since the distance from source to target is initially at most n, therefore the total number of iterations is bounded by n times m, with another factor of m coming from Dijkstra's algorithm. So to summarize, Edmonds-Karp is a variant of Ford-Fulkerson algorithm. It's actually an algorithm, it's fully specified, and it runs in polynomial time. Okay, so and here we take a short break, and I ask you to answer the quiz by stating your student ID. Okay, and while you keep recording attendance, let's resume the lecture and apply our algorithm, the Ford-Fulkerson and its refinement. Let's apply that to other graph problems. So here are the slides. Right, so we're going to use Edmonds-Karp here and our runtime analysis to solve the following graph problem. Let's consider the maximum matching problem in bipartite graph. So remember, we talked about complete bipartite graph, and more generally, a bipartite graph is a graph whose vertices can be partitioned into two groups, left, right, or U and V, and edges only run between the different groups, not within a group. So here's an example of a bipartite graph, which is not complete because some edges are obviously missing. So here we have the first class of vertices, we have the second class of vertices, and we have directed edges going from the first class to the second class, but not within second class, nor within the first class. And we consider here more generally the weighted version, but let's first discuss the non-weighted version, where the goal is to find a maximum matching that is a largest subset of the edges that do not share any source nor any target vertex. So the terminology comes from matchmaking, which is a very classical thinking. So imagine U to be candidate husbands and V to be candidate wives, or vice versa. And matchmaking literally means matching candidate husbands to candidate wives for marriage. Yes, as I said, it's an ancient concept, but anyway, the terminology lives on in graph theory. And so a maximum matching is one where we can make as many marriages as possible, of course, while obeying the laws against polygamy. So every husband can be married to only one wife, and every wife can be married to only one husband, which means that no two edges can share a vertex, start vertex, nor a target vertex. So for example, these two edges cannot be simultaneously in a matching, because that means the husband here would be married to 2 wives. And similarly here, this edge and this edge cannot be simultaneously in the matching because it means this wife would be married to 2 husbands. So let me say that again, the matching is a subset of the edges which do not share any start nor any destination vertex. That's a matching. And the maximum matching is the largest subset of the edges. So the original edges set is E, and here we're looking for a subset of the edges. And that already indicates that naive algorithm might try all possible subsets of edges, but there are, of course, exponentially many such subsets. That's the power set of the original edge set. So a naive algorithm is infeasible, is not efficient. Instead, we're looking at a more efficient algorithm. And also we want to consider the more general problem of the weighted maximum matching, namely where the edges are equipped with weights. So here we're not just interested in finding the largest subset of edges, but the subset of edges with largest possible weight, which means that maybe some edges are more important, some marriages are preferred, some weddings are preferred over others. And this is more general because if we just assign a weight 1 to each edge, then we recover the original counting version, the number of marriages, the number of weddings. And by permitting weights in addition, the problem becomes more general. And so it's very interesting that indeed this problem can be solved in polynomial time. Again, illustrating the point that I repeatedly make, that efficient algorithms usually rely on deep mathematical insights. And in this case, namely a reduction of the original problem to a maximum weighted maximum flow problem, which is then solved by calling Edmonds-Karp with its polynomial running time. So let me say it again. The message here is that the weighted maximum bipartite matching problem can be solved in polynomial time, although superficially the specification of the problem refers to exponentially many candidate subsets. This is kind of similar to the minimum spanning tree problem, which also superficially refers to all possible subsets of edges as candidate spanning trees. But yeah, there's still, that's a naive algorithm, but there is a far more efficient polynomial time algorithm. And the idea of this algorithm, yes, as I said, reduce a problem to a flow problem. And this is how we reduce a problem to a flow problem. First let me show you a maximum matching in terms of cardinality. So the green edges, 5 green edges, this is a maximum matching. It is a matching, right? So there's no polygamy happening here. And its maximum, there's no way to get a matching of size 6. Leave that for you to figure out. And anyway, so the approach to generally calculating efficiently such a maximum matching with weight is by adding artificially a source and a target vertex to the graph. So this is kind of applying a transformation to the original bipartite graph. Now this graph is not bipartite anymore, but observe. So let me explain the construction. And we add an edge from the source vertex to any edge, to all edges in the husband set in the first category. And we add an edge from every vertex in the wife category to the sink. Right? So here's everywhere there's an edge. And let's first consider that counting version of the maximum matching problem, where we don't need to worry about weights. And then the observation is that maximum flow from this augmented graph from source to target actually induces a matching, right? So why is that so? Because, right, so there's only one unit of flow going through this edge, and so the maximum flow problem would allow this to be divided here, but since we're talking about integer weights, recall that Ford-Fulkerson and also Edmonds-Karp only return integer valued flows, so it does not divide the flow between these two edges, not half of unit here and half unit here. Instead, it chooses one edge where this one unit of flow that came from the source leaves, passes through, and the same here. In the maximum flow formulation, it would be possible to have flow from here and from here, violating the polygamy condition. So superficially, it seems like a maximum flow does not induce matching, legal matching. But since we assign capacity 1 to this edge, that means either this edge or this edge, exactly one of the incoming edges is actually used by the maximum flow calculated by Edmonds-Karp or Ford-Fulkerson. And this is again a very nice illustration of this principle. Remember, we proved this lemma whenever there's a flow, then there's also an integral flow of same flow value, right? So naively, originally the flow formulation problem admits flows with non-integer values, but we proved using algorithm that whenever there is a flow, then there's also an integer flow of same value. And this is what we use here. The statement that Edmonds-Karp actually calculates an integer flow, and the integer flow actually only has values 0 and 1, not larger values, because we assigned edge weights 1 to these augmented edges from the source and weight 1 to the augmented edges from here. So to summarize, by augmenting the graph, we can now invoke Edmonds-Karp to calculate the maximum flow, and from this maximum integer flow, look at the edges which are used between in the bipartite graph. Ignore the augmented edges, look only at the edges in the bipartite graph, and pick those who carry flow 1. And as just argued, these are then guaranteed to constitute a matching. Okay, so to summarize, one can calculate maximum matching in bipartite graphs, and that's an important restriction. Okay, so there's also a very famous algorithm for calculating maximum matchings in non-bipartite graphs, but this is a very complicated algorithm and postponed to CS300 advanced algorithms. So that's kind of a cross promotion for you. Please consider attending CS500 when you're ready after graduating. Okay, so to summarize, now we have applied Edmonds-Karp to solve the maximum bipartite matching problem here. And let's now oh, here's a great question in the chat. Thank you so much. If we switch U and V, right, can the matchings differ? Well, intuitively, they cannot, right? So if we replace husbands and wives, then by symmetry of a marriage, then the same marriages are still possible, and therefore also the same maximum matchings. Yes, that's kind of a physicist's argument. Thanks for this great question. Okay, as I said, and this is going to be the last slide of today's lecture. Now we're applying the Ford-Fulkerson algorithm to another graph problem, namely the minimum cut problem. So what is minimum cut? In the minimum cut problem, as usual, we're given a graph, a weighted graph with non-negative integer edge weights, and we're given a start and target vertex. And let me first explain to you what is a cut in such a graph. A cut is a partition of the vertices into two parts. So you see that here, the green part and the blue part. The graph has 6 vertices, and we partition it into the green and into the blue. And so this partition, for simplicity, we also, so here the partition is called X and Y, but for simplicity, we only consider X, and every vertex that is not in X is implicitly considered to be part of Y. So partition here is, for simplicity, just a subset of the vertices, and this is what we call a cut. A cut is a subset of the edges induced by such a partition. So the partition refers to the vertices, the green and the blue vertices, and the cut of this partition are the edges that go from the green to the blue vertices. Not within the green, nor within the blue, but only edges going from green to blue. That's a cut. Well, let me say that again. We have a partition of the vertices, and the partition of the vertices induces a cut, which is a subset of the edges. Which edges? Those edges that go from the first part of the partition of vertices to the second part of the partition of vertices. Not the edges that remain within the first part, not the edges that remain in the second part. So here we've defined formally a cut in the graph from source to target is a subset of the vertices, namely implicitly partition. Those vertices that belong to the subset C must include the source vertex, and those vertices which do not belong to C constitute the other part of the partition, and this part must include the target vertex T, particularly T must not belong to this subset of vertices. So that's a cut, and a cut induces a subset of the edges, namely those edges, you see it, those edges, these are all edges, right? Those edges that go from the left part, from the green part of the subset of vertices, to the right part, to the blue part, to those vertices which are not part of the cut. So, and the capacity of a cut is the sum of the capacities of all edges thus induced. So in this example, the capacity of this cut is 4 plus 3, because this edge has capacity 4, this edge has capacity 3, and the edges in the green part don't matter, and the edges inside the blue part don't matter. So this is a total capacity. Here's another example. So this is the same graphic actually as you see here, but a different cut. So this time the cut here is X drawn in green, right? And the remaining vertices that are not part of this cut are here again drawn in blue. So this are times it's 2 vertices here and 4 vertices here. And the edges that go from the first part to the second part are this edge with capacity 4 and this edge with capacity 4, but not this edge, because this edge is going in the wrong direction. So that's important, subtle but important point here. So here we really consider only edges that go from the part that contains the source vertex to the part that contains the target vertex, but not edges that go the other way around. And the capacity is the sum of the capacities of those edges 4 plus 4, but not including 3. Okay, so this defines the capacity of a cut. And the goal is here to minimize the capacity of a cut, to find a cut which has minimum capacity. Okay. So previously we considered the maximum flow problem, which is a maximization problem. But here we consider a minimization problem, namely find a minimum cut. But the cut must, of course, include the source vertex, right? So it must there must be some edges, and therefore there must be some edge weights. And so that's the goal. That's a computational problem. Now we have finally finished the specification. Yes, I keep emphasizing the importance of having a full specification of the problem before even starting to consider algorithmic or other solutions to the problem. And here we've arrived at the specification. Input is the graph, directed graph with non-negative integer weighted edges and a source and a target vertex. And the goal is to calculate a minimum cut, a minimum subset of the vertices, such that all the edges leaving that subset, right, leaving that subset and therefore entering the complement, together their capacity is minimal. Okay, so and yes, that's a goal. Output a subset of the edges which constitute a minimum cut between source and target. And again, this algorithmic problem seems to be involved because again, superficially it seems to involve all possible subsets of vertices or of edges, of which there are exponentially many. But mathematics comes to the rescue because of this famous max flow min cut theorem. This is a purely mathematical theorem that says the value of a minimum cut is equal to the value of a maximum flow. And that theorem puts us into business algorithmically, right? Because we have an algorithm that calculates the maximum flow, and according to the theorem, that also constitutes a minimum cut. So we can solve the minimum cut problem using Edmonds-Karp / Ford-Fulkerson in polynomial time, which is far from obvious if you don't know all the algorithm. Right? So let's for the last part of today's lecture, prove this theorem. This is one of the cases where I actually prove a purely mathematical theorem, because the proof is really nice and elegant and algorithmic. So I really like this and emphasize this play and mutual support between mathematics and computer science. Mathematics gives rise to efficient algorithms, and conversely, interestingly, algorithms give rise to claims in pure mathematics that have nothing to do with algorithms, such as, for example, that row rank is equal to column rank, which is proven using Gaussian elimination algorithm, although the statement has nothing to do with algorithms. Or statement that every flow in a graph with integer weights has an equivalent flow which is only uses integer capacities. And thirdly, here the max cut minimum flow theorem, which says that two quantities that are purely mathematical coincide, and we see that one part of the proof involves actually Ford-Fulkerson algorithm. So the one direction, so the statement is about an equation, an equality, right? And we often prove equality by proving two inequalities, and that's what we're going to do here. The first inequality is kind of easy, namely since right, so consider any cut, like this cut, right? Then by the very definition of a cut, anything that flows into the source must somehow pass through the cut, right? So imagine this to be the cut, and anything that flows into here must at some point, maybe divided, partitioned into different edges, but in total it must pass through that edges considering the cut before ending up in the target. Therefore, it is kind of obvious that every cut satisfies that the value of a minimum cut must be at most greater or equal to the value of a maximum flow. Let me say that again. A maximum flow must pass through any cut, and therefore must pass in particularly through the minimum cut, and therefore must be less or equal to the value of a minimum cut. And the interesting equality is the opposite one. And this is the equality which we prove using Ford-Fulkerson. Namely, we make a thought experiment. Suppose we have run Ford-Fulkerson. So efficiency doesn't matter here. It's just to prove a mathematical statement. But let's just suppose we have run Ford-Fulkerson, and Ford-Fulkerson has produced a maximum flow, which we already know. And let's consider the residual graph. Remember, the residual graph is the graph consisting of all the edges that have not yet been exhausted in their capacity. Right? And so we consider this graph, and then in this graph that has some edges removed from the original graph, those edges that have already been exhausted, right? And then we consider the reachability problem in this subgraph from start vertex S, which vertices can still be reached in this residual graph. And let's denote this subset of vertices with C. And this is by the very definition a cut, right? And now consider the edges that go from this cut out, right? Like in this example, let's say this is the cut, and consider the edges that go out. Then, as I just said, the flow or any cut must have value less or equal to this flow, and therefore the other equality of the minimum cut maximum flow theory follows. So that ends our chapter 5 on graph problems and algorithm for graph problems. Let's have a look and review of the content of chapter 5. So chapter 5 is about graph problems. We have talked about different types and classes of graphs, undirected graphs, weighted graphs. We've talked about diameter of graph. We talked about degree of graph, complete graphs, and yeah, various properties of graphs, planarity of graphs. Then we started talking about graph problems and algorithms, such as shortest path problem, variant, the single source shortest path problem, Then we talked about the single source all target problems. And then we talked about the all pairs problem, shortest path. Then we talked about the minimum spanning tree problem. Again, first specifying the problem, calculate a minimum spanning tree. And we discussed two algorithms, Prim's algorithm and Kruskal's algorithm. And we talked about the data structures or data types that underlie Prim's algorithm and that underlie Kruskal's algorithm. In case of Prim's algorithm, it's a priority queue. In the case of Kruskal's algorithm, it's a so-called union find or disjoint forest data structure. And we've analyzed the computational cost of both algorithms, and we've compared them and determined in which cases Prim's algorithm is preferable, more efficient, and in which cases Kruskal's algorithm is is more efficient. Then we started today, last time we discussed the maximum flow problem, which we've reviewed today, the Ford-Fulkerson algorithm, which is not technically an algorithm for solving the problem. It's not an algorithm because it doesn't specify which augmenting path to choose. And if the choice of augmenting path is unfortunate, then Ford-Fulkerson has an exponential number of iteration, namely exponential in the binary length of the input, which means linear in the value of the final maximum flow. And then we discussed Edmonds-Karp's refinement of Ford-Fulkerson, where the augmenting path is chosen to be a shortest path. And we showed that with this choice, the running time of the algorithm does become polynomial n times m squared. And then we discussed other graph problems that can be solved efficiently using Edmonds-Karp, namely the maximum weighted bipartite matching problem, for which otherwise it seems very difficult to design an algorithm. So we used a technique called reduction. We did not discuss the famous Edmonds algorithm for non-bipartite maximum matching. And we discussed the minimum cut problem that was the last slide we've just seen, which again can be solved using Edmonds-Karp according to the max flow minimum cut theorem, a purely mathematical theorem. So that's all for today. And the next lecture we'll start talking about string problems and string algorithms.